For this inelastic collision example, I figured it would be good to take a look at a problem that had numerical values in it. We have a 2 kilogram object moving to the left at 4 meters per second, strikes a 24 kilogram object which was initially moving to the left at 0.5 meters per second. If the 24 kilogram object moves to the left at 1 meter per second after the collision, what is the velocity of the 2 kilogram object after the collision? What I'm going to do here is I'm just going to draw just a little picture just so we can see what's going on. We have this 2 kilogram object which is moving to the left at 4 meters per second initially, and then we have this 24 kilogram object, which is obviously not to scale, which is moving to the left at 1 meter per second. After the collision, so this is before, after the collision, we have this, oops, sorry, initially this was moving at 0.5, I mislabeled that. After the collision, we have the 24 kilogram object moving to the left at 1 meter per second. And then we don't know how fast the 2 kilogram object will be moving. We do know it's an inelastic collision, so we do know that they are going to bounce off of each other, which means we don't have to worry about combining them together. We also know that it's not elastic, so we don't have to worry about our kinetic energy for this problem, although we probably will take a look at that later just so we can see what the kinetic energy would look like for this collision. Just to begin then, we know that the momentum of object A, let me just call the 2 kilogram object A and the 24 kilogram object B, just to clarify. We know the momentum of A before plus the momentum of B before is equal to the momentum of A after plus the momentum of B after, which means if I were to split this up, I know that the mass of A times the velocity of A plus the mass of B times the velocity of B is going to equal the mass of A times the new velocity of A plus the mass of B times the new velocity of B. I need to make sure that I keep my direction straight here though. I need to focus on whether I have a positive direction or a negative direction. And typically I will treat to the right as positive and to the left as negative. What this means is that both objects initially are moving to the left, so they both have a negative initial velocity. If I plug in the values that I have, object A has a mass of 2 kilograms, initial velocity of -4 meters per second. Object B has a mass of 24 kilograms and an initial velocity of -0.5 meters per second. Then afterwards, I know that object A still has a mass of 2 kilograms. I don't know what the velocity of A is. Mass B has a mass of 24 kilograms still and has a velocity of -1 meters per second because it's moving to the left at 1 meter per second, which means all I really need to do is to solve this for A, which means if I add up what I have on the left, I have -20 as my total momentum, -20 kilograms meters per second. That's going to equal 2 kilograms times the new velocity of A minus 24 kilograms meters per second. If I add 24 kilograms meters per second to both sides, then divide by 2, I get a new velocity of A of 2 meters per second, which means that it's moving 2 meters per second to the right. So that sign matters as well. Now, if I wanted to look at the kinetic energy involved in this situation, which isn't a bad idea, what I could say is I know that the kinetic energy, if I look at the total kinetic energy of the system before, that's going to be the kinetic energy of A plus the kinetic energy of B before the collision, which means 1/2 mass of A times the velocity of A squared plus 1/2 mass of B times the velocity of B squared, which means if I plugged in the values here, it'd be 1/2 times 2 kilograms times -4 meters per second squared plus 1/2 times 24 kilograms. That would be times -0.5 meters per second, per second squared, which means if I calculated this, I would get a total kinetic energy of 19 joules. Now, if I looked at after the collision, it'd be the new kinetic energy of A plus the new kinetic energy of B, which means it'd be 1/2 times 2 kilograms times 2 meters per second, the quantity squared, plus 1/2 times 24 kilograms times -1 meter per second, the quantity squared, which would give me a total of 16 joules. The reason that's important is we know that the kinetic energy is not the same after the collision as before, which means we know that the collision is not elastic. The other thing to keep in mind here is that you should be getting a kinetic energy after the collision that's less than the kinetic energy before the collision. It's not going to have a creation of kinetic energy with this collision. So that is kind of an important key to keep in mind. I wouldn't be surprised if that would be a question on the AP test at some point, asking how do you know if this collision is a valid collision or not? And you could say not only is momentum conserved, but it's also important to take a look at the total energy and say, well, if it's creating energy, that can't happen. That's not a good collision. But if it's losing some kinetic energy, that could be going to thermal energy, that could be going to sound energy, so we know that that could work out. So that's just something to keep in mind because that would be something possibly on a free response question on the AP test.